An acid is a chemical substance whose aqueous solutions are characterized by a sour taste, the ability to turn blue litmus red, and the ability to react with bases and certain metals to form salts. An aqueous solution of an acid has a pH of less than 7 and is colloquially also referred to as acid, while the strict definition refers only to the solute. An acid usually contains a hydrogen atom bonded to a chemical structure that is still energetically favorable after loss of H+. A lower pH means a higher acidity, and thus a higher concentration of positive hydrogen ions in the solution. Chemicals or substances having the property of an acid are said to be acidic. There are three common definitions for acids: the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. The Arrhenius definition defines acids as substances which increase the concentration of hydrogen ions, or more accurately, hydronium ions, when dissolved in water. The Bronsted-Lowry definition is an expansion to include solvents other than water. An acid is a substance which can act as a proton donor. By this definition, any compound which can be deprotonated can be considered an acid. Examples include alcohols and amines which contain OH or NH fragments. A Lewis acid is a substance that can accept a pair of electrons to form a covalent bond. Examples of Lewis acids include all metal cations, and electron-deficient molecules such as boron trifluoride and aluminium trichloride. Common examples of acids include hydrochloric acid, acetic acid, sulfuric acid, and tartaric acid. As these examples show, acids can be solutions or pure substances, and can be derived from solids, liquids, or gases. Strong acids and some concentrated weak acids are corrosive, but there are exceptions such as carboranes and boric acid. Definitions and concepts. Modern definitions are concerned with the fundamental chemical reactions common to all acids. Most acids encountered in everyday life are aqueous solutions, or can be dissolved in water, so the Arrhenius and Bronsted-Lowry definitions are the most relevant. The Bronsted-Lowry definition is the most widely used definition, unless otherwise specified. Acid-base reactions are assumed to involve the transfer of a proton from an acid to O base. Hydronium ions are acids according to all three definitions. Interestingly, although alcohols and amines can be Bronsted-Lowry acids, they can also function as Lewis bases due to the lone pairs of electrons on their oxygen and nitrogen atoms. Arrhenius acids. The Swedish chemist Svante Arrhenius attributed the properties of acidity to hydrogen ions or protons in 1884. An Arrhenius acid is a substance that, when added to water, increases the concentration of H+ ions in the water. Note that chemists often write H+ and refer to the hydrogen ion when describing acid-base reactions, but the free hydrogen nucleus, a proton, does not exist alone in water. It exists as the hydronium ion H3O+. Thus, an Arrhenius acid can also be described as a substance that increases the concentration of hydronium ions when added to water. This definition stems from the equilibrium dissociation of water into hydronium and hydroxide ions. H2O plus H2O H3O plus O-. In pure water the majority of molecules are H2O, but the molecules are constantly dissociating and reassociating, and at any time a small number of the molecules are hydronium and an equal number are hydroxide. Because the numbers are equal, pure water is neutral. An Arrhenius base, on the other hand, is a substance which increases the concentration of hydroxide ions when dissolved in water, hence decreasing the concentration of hydronium. The constant association and dissociation of H2O molecules forms an equilibrium in which any increase in the concentration of hydronium is accompanied by a decrease in the concentration of hydroxide. Thus an Arrhenius acid could also be said to be one that decreases hydroxide concentration, with an Arrhenius base increasing it. In an acidic solution, the concentration of hydronium ions is greater than 10⁻⁷ moles per liter. Since pH is defined as the negative logarithm of the concentration of hydronium ions, acidic solutions thus have a pH of less than 7. Bronsted-Lowry acids. While the Arrhenius concept is useful for describing many reactions, it is also quite limited in its scope. In 1923, chemists Johannes Nicolaus Bronsted and Thomas Martin Lowry independently recognized that acid-base reactions involve the transfer of a proton. A Bronsted-Lowry acid is a species that donates a proton to a Bronsted-Lowry base. Bronsted-Lowry acid-base theory has several advantages over Arrhenius theory. Consider the following reactions of acetic acid, the organic acid that gives vinegar its characteristic taste. CH3COOH plus H2O, CH3COO minus plus H3O plus CH3COOH plus NH3, CH3COO minus plus NH plus. For both theories easily describe the first reaction. CH3COOH acts as an Arrhenius acid because it acts as a source of H3O+ when dissolved in water, and it acts as a Bronsted acid by donating a proton to water. In the second example, CH3COOH undergoes the same transformation, in this case donating a proton to ammonia, but cannot be described using the Arrhenius definition of an acid because the reaction does not produce hydronium. Bronsted-Lowry theory can also be used to describe molecular compounds, whereas Arrhenius acids must be ionic compounds. Hydrogen chloride and ammonia combine under several different conditions to form ammonium chloride, NH4Cl. In aqueous solution, hydrogen chloride behaves as hydrochloric acid and exists as hydronium and chloride ions. The following reactions illustrate the limitations of Arrhenius's definition. H3O plus Cl minus plus NH3Cl minus plus NH4 plus H2O. Hydrogen chloride plus NH3NH4Cl. Hydrogen chloride plus NH3NH4Cl. As with the acetic acid reactions, both definitions work for the first example, where water is the solvent and hydronium ion is formed by the hydrogen chloride solute. The next two reactions do not involve the formation of ions but are still proton transfer reactions. In the second reaction, hydrogen chloride and ammonia react to form solid ammonium chloride and a benzene solvent, and in the third, gaseous hydrogen chloride and NH3 combine to form the solid Lewis acids. A third concept was proposed in 1923 by Gilbert N. Lewis, which includes reactions with acid-base characteristics that do not involve a proton transfer. A Lewis acid is a species that accepts a pair of electrons from another species. In other words, it is an electron pair acceptor. Bronsted acid-base reactions are proton transfer reactions, while Lewis acid-base reactions are electron pair transfers. All Bronsted acids are also Lewis acids, but not all Lewis acids are Bronsted acids. Contrast how the following reactions are described in terms of acid-base chemistry. In the first reaction, a fluoride ion, F-, gives up an electron pair to boron trifluoride to form the product tetrafluoroborate. Fluoride loses a pair of valence electrons because the electrons shared in the B-F bond are located in the region of space between the two atomic nuclei and are therefore more distant from the fluoride nucleus than they are in the lone fluoride ion. BF3 is a Lewis acid because it accepts the electron pair from fluoride. This reaction cannot be described in terms of Bronsted theory because there is no proton transfer. The second reaction can be described using either theory. A proton is transferred from an unspecified Bronsted acid to ammonia, a Bronsted base. Alternatively, ammonia acts as a Lewis base and transfers a lone pair of electrons to form a bond with a hydrogen ion. The species that gains the electron pair is the Lewis acid. For example, the oxygen atom in H3O+ gains a pair of electrons when one of the HO bonds is broken and the electrons shared in the bond become localized on oxygen. Depending on the context, a Lewis acid may also be described as an oxidizer or an electrophile. Organic acids, such as acetic, citric, or oxalic acid, are not Lewis acids. Dissociation and equilibrium. Reactions of acids are often generalized in the form HH++ A-, where H represents the acid and A- is the conjugate base. This reaction is the protolysis. Acid-base conjugate pairs differ by one proton, and can be interconverted by the addition or removal of a proton. Note that the acid can be the charged species and the conjugate base can be neutral, in which case the generalized reaction scheme could be written as H plus H plus A. In solution there exists an equilibrium between the acid and its conjugate base. The equilibrium constant K is an expression of the equilibrium concentrations of the molecules or the ions in solution. Brackets indicate concentration, such that H2O means the concentration of H2O. The acid dissociation constant K is generally used in the context of acid-base reactions. The numerical value of K is equal to the product of the concentrations of the products divided by the concentration of the reactants, where the reactant is the acid and the products are the conjugate base and H+. The stronger of two acids will have a higher K than the weaker acid. The ratio of hydrogen ions to acid will be higher for the stronger acid, as the stronger acid has a greater tendency to lose its proton. Because the range of possible values for K spans many orders of magnitude, a more manageable constant, pKa, is more frequently used, where pKa equals log 10 K. Stronger acids have a smaller pKa than weaker acids. Experimentally determined pKa at 25 degrees Celsius in aqueous solution are often quoted in textbooks and reference material. Nomenclature. In the classical naming system, acids are named according to their anions. That ionic suffix is dropped and replaced with a new suffix, according to the table below. For example, hydrogen chloride has chloride as its anion, so the "-ide suffix makes it take the form hydrochloric acid. In the IUPAC naming system, aqueous is simply added to the name of the ionic compound. Thus, for hydrogen chloride, the IUPAC name would be aqueous hydrogen chloride. The prefix hydro is added only if the acid is made up of just hydrogen and one other element. Classical naming system. Acid strength. The strength of an acid refers to its ability or tendency to lose a proton. A strong acid is one that completely dissociates in water. In other words, 1 mole of a strong acid H dissolves in water, yielding 1 mole of H+ and 1 mole of the conjugate base, A-, and none of the protonated acid H. In contrast, a weak acid only partially dissociates, and at equilibrium both the acid and the conjugate base are in solution. Examples of strong acids are hydrochloric acid, hydroiodic acid, hydrobromic acid, perchloric acid, nitric acid and sulfuric acid. In water each of these essentially ionizes 100%. The stronger an acid is, the more easily it loses a proton, H+. Two key factors that contribute to the ease of deprotonation are the polarity of the H-A bond and the size of atom A, which determines the strength of the H-A bond. Acid strengths are also often discussed in terms of the stability of the conjugate base. Stronger acids have a larger K and a more negative pKa than weaker acids. Sulphonic acids, which are organic oxyacids, are a class of strong acids. A common example is toluene sulphonic acid. Unlike sulfuric acid itself, sulphonic acids can be solids. In fact, polystyrene functionalized into polystyrene sulfonate is a solid strongly acidic plastic that is filterable. Superacids are acids stronger than 100% sulfuric acid. Examples of superacids are fluoroantimonic acid, magic acid and perchloric acid. Superacids can permanently protonate water to give ionic, crystalline hydronium salts. They can also quantitatively stabilize carbocations. While Ca measures the strength of an acid compound, the strength of an aqueous acid solution is measured by pH, which is an indication of the concentration of hydronium in the solution. The pH of a simple solution of an acid compound in water is determined by the dilution of the compound in the compound's Ca. Chemical characteristics. Monoprotic acids. Monoprotic acids are those acids that are able to donate one proton per molecule during the process of dissociation as shown below. Ha plus H2O H3O plus A minus Ca. Common examples of monoprotic acids in mineral acids include hydrochloric acid and nitric acid. On the other hand, for organic acids the term mainly indicates the presence of one carboxylic acid group, and sometimes these acids are known as monocarboxylic acid. Examples in organic acids include formic acid, acetic acid and benzoic acid. Polyprotic acids. Polyprotic acids, also known as polybasic acids, are able to donate more than one proton per acid molecule. In contrast to monoprotic acids that only donate one proton per molecule, specific types of polyprotic acids have more specific names, such as diprotic acid and triprotic acid. A diprotic acid can undergo one or two dissociations depending on the pH. Each dissociation has its own dissociation constant, Ca1 and Ca2. H2A plus H2O H3O plus Ha minus Ca1 Ha minus plus H2O H3O plus A2 minus Ca2. The first dissociation constant is typically greater than the second, i.e., Ca1 greater than Ca2. For example, sulfuric acid can donate one proton to form the bisulfate anion, for which Ca1 is very large. Then it can donate a second proton to form the sulfate anion, wherein the Ca2 is intermediate strength. The large Ca1 for the first dissociation makes sulfuric a strong acid. In a similar manner, the weak unstable carbonic acid can lose one proton to form bicarbonate anion and lose a second to form carbonate anion. Both Ca values are small, but Ca1 greater than Ca2. A triprotic acid can undergo 1, 2, or 3 dissociations and has 3 dissociation constants, where Ca1 greater than Ca2 greater than Ca3. H3A plus H2O H3O plus H2A minus Ca1 H2A minus plus H2O H3O plus HA2 minus Ca2 HA2 minus plus H2O H3O plus A3 minus Ca3. An inorganic example of a triprotic acid is orthophosphoric acid, usually just called phosphoric acid. All 3 protons can be successively lost to yield H2PO4-, then HPO42-, and finally PO43-. The orthophosphate ion, usually just called phosphate. Even though the positions of the 3 protons on the original phosphoric acid molecule are equivalent, the successive Ca values differ since it is energetically less favorable to lose a proton if the conjugate base is more negatively charged. An organic example of a triprotic acid is citric acid, which can successively lose 3 protons to finally form the citrate ion. Although the subsequent loss of each hydrogen ion is less favorable, all of the conjugate bases are present in solution. The fractional concentration, alpha, for each species can be calculated. For example, a generic diprotic acid will generate 3 species in solution, H2A, Ha-, and A2-. The fractional concentrations can be calculated as below when given either the pH or the concentrations of the acid with all its conjugate bases. A plot of these fractional concentrations against pH for given K1 and K2 is known as a Bjerrum plot. A pattern is observed in the above equations and can be expanded to the general N-protic acid that has been deprotonated I times, where K0 equals 1 and the other K terms are the dissociation constants for the acid. Neutralization. Neutralization is the reaction between an acid and a base, producing a salt and neutralized base. For example, Hydrochloric acid and sodium hydroxide form sodium chloride and water. Hydrogen chloride plus NaOH, plus NaCl. Neutralization is the basis of titration, where a pH indicator shows equivalence point when the equivalent number of moles of a base have been added to an acid. It is often wrongly assumed that neutralization should result in a solution with pH 7.0, which is only the case with similar acid and base strengths during a reaction. Neutralization with a base weaker than the acid results in a weakly acidic salt. An example is the weakly acidic ammonium chloride, which is produced from the strong acid hydrogen chloride and the weak base ammonia. Conversely, neutralizing a weak acid with a strong base gives a weakly basic salt, e.g., sodium fluoride from hydrogen fluoride and sodium hydroxide. Weak acid-weak base equilibrium. In order for a protonated acid to lose a proton, the pH of the system must rise above the pKa of the acid. The decreased concentration of H+ in that basic solution shifts the equilibrium towards the conjugate base form. In lower pH solutions, there is a high enough H+ concentration in the solution to cause the acid to remain in its protonated form. Solutions of weak acids and salts of their conjugate bases form buffer solutions.